So in this case, we are going to consider an exam revision, considering our AC machines. We have this April 2024 exam where we are given on question number 5. 5.1, you're given to name two methods used to connect the stator windings of a three-phase induction motor electrically. How do you connect? So these, we do understand it can be in a stator, or you can with these stator windings, they can be connected in a star, or they can be in a delta. These are the connections of a three-phase. So they're just asking you the three-phase connections electrically, how the stator windings are going to be. So we can have the star connection, we can have the delta connection in our simplification. So this was a straightforward question. And considering 5.2, a 525 volt 6-pole 50 hertz 3-phase delta connected induction motor. All right, let's try to figure out this information that we are given here on 5.2 according to the data that we are given. A 525, what does it mean? This is simply the line voltage that we are given there. 6-pole 50 hertz 3-phase delta connected. They are giving you line values. So you've got the line voltage that you are given, which is 525 volts, and the 6-pole there, the number of poles, there are 6. So it's a 6-pole, meaning to say the pairs. How many pairs do we have? The number of pair poles you have to divide. 6 divided by 2, meaning to say we have got 3 pairs from that. 3-phase, as we do understand, this is a 3-phase, and it's also delta connected. All right. In delta connection, what is it that we understand in terms of the voltages, in terms of the currents? In a delta, voltage is the same. The line voltage, remember, that is your phase voltage. But the line current is equal to the square root of 3 of the what? The phase. That is the condition of a delta. So you have to consider that. So they are saying the induction motor develops 28 kilowatts when running at the, meaning it's still running. This is the power that is being developed while running. So this is the rotor power that we are given there. While least, remember when running, the speed, you consider the rotor speed. When running, the speed there is the rotor speed, meaning that the power also there is the rotor power that we are given of 28 kilowatts. So take note there, because the power is supposed to be, there is output, but this is the output of the rotor when considering the rotation while it is running, because there is that mechanical power, which is the output at the end. So you must be careful on this one. This is not the one that you're given. This is the output, yes, but of the rotor. So you consider as the rotor power at a speed of, this is the speed of the rotor also when running. So that is 950 revs per minute. Then we are given later on the rotor ion loss is negligible, meaning to say we cannot consider the rotor ion losses, and the friction, okay, this one is on its own, and that's another part. The friction loss in the bearings is, then we are given the part of what? The friction. But you have to neglect the ion loss, then the friction loss is considered there. That is the friction loss was going to be 800 watts. So 800 watts, we can even write to kilowatts, since we are given the other power in kilowatts, just divide by 1000, which is going to be 0.8 kilowatts for a power factor of 0.8 lagging. So we are also given the power factor of 0.8 lagging. That is what we had. So like I was saying, this issue of the power, we're going to see it when we consider the calculations there, because the power, remember, when you're dealing with three-phase induction motors, the induction motor losses and efficiencies are affected as you enter the stator. You are going to have the stator losses. As you are in the rotor, the part of the rotor, you're going to have the rotor losses, which is part of the rotor copper losses. Then we have got the friction up to the power, which is where we consider the useful mechanical power at the end, which is considering to say after the rotor here, there's the rotor power. This is the one that we are given. And just in between these, there are losses that are there, which is considered the friction and windage loss, all those friction and windage losses. So there we are going to consider friction and windage losses, part of wind, which is the windage losses there. Before you get to the what? Before you get to the output, the power that is going to be here, you can write as PM or you can write as P out, which is the mechanical power at the end there. So that was important for you to know that this is not the output. This one, while running the rotor power, then we've got the output when the losses now are considered. All right, no problem. Let's consider our questions. Let's see how we're supposed to attempt these questions. 5.21, the percentage slip. They need the percentage one at which the motor is operating. So we do understand that the percentage slip taken from per unit slip, we can obtain the percentage from there. So the percentage slip is going to be the ratio that we have of NS, which is our synchronizing, minus NR for the rotor speed, everything over NS. All right, so this is percentage. So you're going to multiply by what? By 100%. If it was per unit, you just ignore that and calculate your per unit value. So that is it. Let us consider our calculations. We have the NR, the rotor speed is there, but NS we do not have, considering this NS can be calculated. Remember, there is frequency. We have got the frequency. We have to consider the part of our frequency. Okay, I think I left that part of our frequency. So let's check here. Remember also the frequency, we are given 50 hertz there. So we have our frequency there. So we're going to have our frequency of 50 hertz. So this one is there. So having the frequency, we can calculate our NS, which is the speed to be considered in our calculation. So as we can see, guys, we need the part of what? Of the synchronous speed. That is going to be NS. The other speed is given in revs per minute, your rotor speed. So use the formula, the one that will give you per minute. So you're going to use 60F instead of just using F over P. Use this as 60F to obtain the revs per minute. So this is simply, guys, a matter of substituting into the formula, because we have the frequency at what? At 50 hertz, and the number of pair poles, the pairs, P there is the pair poles, which is what? Which is 3. That was going to give us the speed in that case, and that was going to be 1000 revs per minute. So this is 1000 revs per minute. So taking this into consideration and the one that you're already given, your NR there, you're going to obtain the percentage slip. So our NS, that is 1000, minus our NR, which is 950 over 1000. This is just a repetition, as you can see, times 100%. So meaning to say we are going to obtain our percentage slip from there, and that was going to be 5%. So you must be careful in your simplifications or calculations that you are going to have. This is percentage, where we can obtain per unit value from there. You can also obtain per unit by dividing by 100 to have what? Per unit value. So that is it, guys. All right. So our percentage slip, it was 5%. Let's consider the other question that we are given. In this case, they want you to determine or to calculate the rotor copper loss. The rotor copper loss. Remember from the formulas of the rotor copper loss, actually, when you're considering the issue of the rotor input and the rotor output, so many formulas that we actually put into consideration there. So many formulas that we put where the rotor copper loss is. If we are given the rotor input, let's say we have the rotor input, we are going to consider the rotor copper loss over what? Over the slip. We do not have the rotor input. So you cannot consider that. From the output, we do understand that. We could also consider that from the rotor output, which is equal to the rotor input into 1 minus the slip. But we do not have the rotor input. So this cannot work. Also, from the same thing, the rotor output, considering our rotor output, it is equal to the rotor copper loss into 1 minus S over S, which is the slip. So meaning to say this can work because we need the rotor copper loss and we have the rotor output. Remember the rotor output there, PR is there. So this formula was going to work. All right, so let's consider this formula, like I said, from the three formulas, which are of the rotor input and the rotor output. You're going to choose one. So from there, we're going to use this one of the rotor output. The rotor output equal to the rotor input. So we're going to use the rotor input loss, which is the one that we need there over what? 1 minus slip over slip. This is per unit slip that you are considering. So the question is needing you to calculate what? The rotor copper loss. That is the rotor copper loss. Why am I writing this, guys? The rotor copper loss there. This is the one that we need there. So let us substitute and see what we have. And because we have got the rotor output, this is our PR, this one. The rotor copper loss is the one that we need to determine. The slip, this one is per unit slip that you have to consider. So you divide this one by what? By 100. Remember, converting to per unit values. So that was it, guys. Let us substitute. We have it. We're going to make even the subject. We can just divide by this bracket, both sides. 1 minus S over S. Divide also this side. So by dividing, we are making the rotor copper loss to be the subject. So meaning to say our rotor copper loss can be determined. So the rotor copper loss is equal to what? The rotor output from the rotor, we have got our PR there, which is 28 kilowatts. So this was going to be 28 kilowatts, which is 28 times 10 to the exponent of 3 over what? 1 minus the per unit slip. Remember, it was 5%. So if you divide that 5% by 100, it was going to be 0.05, something like that. So that's 1 minus 0.05 over 0.05. As you can see, that one is just a repetition here. So this is it. You're going to obtain the rotor copper loss from there. We can make the subject of the formula from that. We can play around and have our rotor copper loss. So meaning to say, your rotor copper loss at the end is going to be, it was going to be 1473.684. Can even write to kilowatts, divide by 1000, it's going to be 1.47. This is going to change into 474 in what? In kilowatts. So you can have it like that, which is your rotor copper loss. So if you had taken that as the output power now of everything, it means it was gonna have an effect there. It was going to have an effect on your calculations. So you have to be very careful, guys, as you consider your calculations. So that's our 5.22. So we need the rotor copper loss. Just gonna have this one aside so that in case of when we need this value, we are just gonna use it. So the rotor copper loss, we obtained 1.474 kilowatts. Let's check another question that you're given there, which is determining or to calculate the power input to the motor now. The power input. If the total losses occurring in the stator amounts to, so we have got the losses of the stator also. So 5.23, we need the input power. given the losses, which are the total losses occurring in the stator. So these are stator losses that we are given there. They amount to 1080 watts. So just divide by 1000 to convert to kilowatts. It's going to be 1,08 kilowatts, since the other power that we are given or the other losses are in kilowatts. So the question is, we need to determine the input. What will be the input? It will be best for us to analyze this diagram, because the input is here. This is where you have your input. You enter the stator, where there are stator losses as we are given there. We've got the losses which are occurring in the stator, the rotor, considering the rotor losses that are there, which in this case, we are being told here to ignore that part of the rotor ion losses, to be neglected. Then we have the power that is from the rotor, this one, which is our PR. This is the one that we have here. So we are starting from PR here. We need to get to the input. So as you move from these output values going back to the input, you are moving from these output going back to the input. You are going to add the losses. So from output values, to input values, to the input, let's just say to the input value, add losses. So you add the losses, which is vice versa. If you move from the input going to the output, you will be subtracting losses, subtracting. So in this case, we must add the losses that are there in between the output here, the output of the rotor, which is the PR, this one, and this input in between these two. In between these two, which losses do we have in between these two? That is the consideration. So if you take in between the friction and this part of windage losses, is not to be considered. It's not there. It's not there. It's in between. When you move from the rotor output to the actual output, which is our mechanical output there, that's when the friction is to be considered. In between these two, that is where it is. As we are starting from here, going back, we need to go back to the what? Input. So the friction is to be excluded. This part of our friction losses here, it is to be excluded. This one, it is to be excluded. So we are going to add all other losses that we are given, excluding that of friction, because we are starting from what? From the rotor output. As I said, from output values, going back to the input, you are supposed to add. So our input was going to, we add from that rotor output. What are we going to add? The losses that are before this one, before that. What do we have before? That is where we consider the rotor copper loss. Remember, we calculated this, the rotor copper loss. So we're going to consider the rotor copper loss. Remember, we asked, the ion is the one that we asked to neglect, but the rotor copper loss, we calculated this one. We also have what? The stator. Remember, the stator is also there. So we also have the stator losses. These are the ones that we are supposed to consider before here, in between. The rotor here, there will be rotor copper losses here, rotor copper losses, and those ion losses. So the part of the rotor ion losses are the one that you have said neglect, but the rotor copper loss, we cannot neglect this one. We are not told about neglecting that here. They told us to neglect only the rotor ion loss. But the rotor copper loss is to be taken into consideration. So between the rotor output and the input, these are the losses that are there. Between the rotor output, this one going to the mechanical power output, the one that is at the end there is a friction and windage losses, which we are not supposed to include now. We need in between these two, in between the rotor and the input. These are the losses that we are given. So that was your question there. You just have to add, as we have our values which are already in what? In kilowatts. So we're going to use the kilowatts as they are. So our PR is there, 28 kilowatts. So this is 28 plus the rotor copper loss. Remember, we calculated this. That was 1,474 plus the stator losses. Stator losses, we calculated here, it was 1,08. So adding these two, you are now obtaining the input. Remember, you start with the input. As you are in the input, the losses up to the output, they are supposed to be subtracted. So the opposite, as you move from the output going back to the input, you add those losses back. So it was going to be 30,554 kilowatts. So this will be your input power. All right, then with this information, they want you to calculate the current drawn from the supply. The input power is there, so we can consider that, guys. Remember, we have got our input, and this is a three-phase. We are considering what? A three-phase. A three-phase in a dot. We've got the line voltage is there. So you can calculate the current drawn from the supply, which is the line current. Which is the line current. So from the input power, a three-phase, how do you calculate input? How do you calculate power? That will be the square root of 3 times the line voltage times the line current. I'm going to consider the line current and the power factor, which is the cos of phi, like that. Take note, these are not phase values. If you are dealing with the phase values, that way we calculate your power as 3 times. You are using phase values. These are phase in phase. But here we've got line values, so use the square root of 3 instead. So the question is, are we having all this? We are given the line voltage. Input power we calculated. The power factor we're given. Remember? We have the power factor there, the cos of phi. That is your power. Your power factor is there. You need to calculate this current. So let us just make it the subject. So our current dividing everything, we're going to have the square root of 3, the line voltage, and also our power factor. So let's substitute, guys. We have our input power. That's 30,554 kilowatts. So we're going to substitute your input power, 30,554 times 10 to the exponent of 3 over what? The square root of 3. The line voltage, as we had, line voltage as we are given, that was 525. So this is 525 times the power factor. Remember, you're given the power factor there of what? 0,8. So the 0,8 you just take as it is. Remember, cos phi, cos of the angle is the power factor. So already they calculated the power factor for you. There is no need for you to calculate the angle. Then you are going to use cos of that angle. No, already is there, the cos of that. That's your power factor. So that was going to give us the line current of 42.001 to 3 decimal places, or just approximate this one to 42 amps. It is still one and the same. So you could have calculated your power, your current that way. So if you are dealing with the line values there, take note the power square root of 3. If they are phase values, you use what? You use the 3 as it is without a square root. Then from there, they want you to calculate the efficiency of the motor. Efficiency. How are we going to obtain our efficiency? So if we are calculating the percentage efficiency, remember efficiency always, there must be output and input to be considered there, times 100% per percentage value. We have the input, guys. This one we do have, we calculated it. But we're calculating this from where? From the rotor output, not the mechanical or the output of the whole machine. No, it was from the rotor. But if we check properly here, between that rotor here and the output, there is a loss which is there in between, friction and windage losses. Are we given? If we are not given those, it means the rotor output becomes your output. But in this case, we cannot do that because we have them. We have the friction losses. They're there. So we must consider now calculating the output from there, from this rotor going to the output. So which direction are we moving? We are moving the direction of input going to the output. As I said, moving opposite input. As we go this side, you are subtracting. So as you move from this rotor that we have going this side to the output side there, going to the out, you're supposed to subtract the losses which are there. Which losses are there? Friction. You have to remove that. Then we have the output now, that is the overall that is supposed to be used on efficiency. So you must be very careful on that one. You must be very, very careful on this type of equation. So the output can be calculated. The rotor is there. So that is 28 minus the friction. Remember our friction, it was 800 watts converted to kilowatts. That's 0.8. So our output power was going to be 27.2 kilowatts. With this output power and the input starting to the end, you must efficiency because the of everything, the overall from where you started to the ending part. So we cannot end where the rotor is because there are losses after that rotor. So we must subtract those losses to obtain output. Now with that, efficiency can be calculated. So the percentage efficiency was going to be what? Output in kilowatts, that's 27.2 over the input. We're going to have also this in what? In kilowatts, which is 30.554. So with this, efficiency was going to be calculated just like that. So your percentage efficiency in this case was going to give us 89.023%. So this is your percentage efficiency. So let us do as much revisions as we can as we are preparing ourselves for the exams which are ahead of time. We just need to work out more questions, try to figure out those challenging questions, bring them in so that we can have a revision together as we are preparing till we meet again.